Okay, so I thought I'd do a longer analysis here of a system of differential equations. And so we have here a system of two equations. These represent two populations. And so the question is are these like predator-prey, or are these like competing species, or can you tell the difference between those kinds of populations? Well, we see that if we take out the interaction terms, the xy terms, right, then x prime is doing very well. X prime is equal to x, and so that's an exponential growth model. But on the other hand, y prime would be minus 3/4 y, and so that's going to be decreasing. So can you tell what's happening? X is going to be the prey. It does well in the absence of the predator, so y is equal to the predator. Good. And so, of course, the rest of that is that y does well in the presence of the prey, but the prey does not do well in the presence of the predator. Okay, good. All right, so now if we were to do a quick null-Klein analysis, what would we get here? X times 1 minus 1/2 y, and y times minus 3/4 plus 1/4 x. Okay, so in our xy plane, before we do anything, we can just take a look at these. X equals 0, y equals 0, and then y is equal to 1/2, and x is equal to, down here x would be equal to 3, it looks like, huh? Good. So where are the equilibrium solutions? Let's see, is the intersection between x equals 0 and y equals 1/2, is that an equilibrium solution? No, it's not, because that's just where x prime is equal to 0, right? We need one of these and one of those. So we see that we have the origin is one solution, and then between the x, well, these aren't going to match, or these aren't going to intersect, right? And so then we have these two, those two are not going to intersect, and then the intersection of these two lines will be our other one. So we just have our 2. Okay, and so this coordinate was 3/1/2, I believe, right? Or 3/2, actually, 3/2. Good, because again, that's where this line is equal to 0, and so y would have to be 2 to make that work. Okay, good. So now we have our equilibrium solutions. What's next? Linearization, yes, that's right. So in our linearization, we want to construct our Jacobian matrix, which is our f sub x, f sub y, g sub x, g sub y. So in this case, f sub x is going to be 1 minus 1/2 y, and f sub y would be minus 1/2 x. G sub x is going to be 1/4 y, and then g sub y is going to be minus 3/4 plus 1/4 x. Good. And so then we analyze this matrix at each of our equilibrium solutions, and it's nice that we only have 2. At 0, 0, our matrix becomes 1, 0, 0, minus 3/4. And so the trace is equal to 1/4. Determinant is negative 3/4. And so actually you can stop when the determinant is negative, right? Because in the Poincaré diagram, where are you? Yeah, you're down here, and so that's going to be a saddle. Good. Actually, if you know about eigenvalues, you know that the eigenvalues here is just going to be 1 and negative 3/4. And so when you have mixed eigenvalues, you get a saddle. Good. And so the origin is a saddle. And then how about at 3, 2? what do we get? Here, our matrix becomes 1 minus, well, that's going to be a 0, right? And then our minus 3 halves, and then 1 4 1 half, is that right? And then x being 3, we'll zero this one out. Good. And so we look at our trace. Can you guys still read that? I can't see the window right there. Yes, good. So our trace is 0. Determinant 0 minus 3/4 is 3/4. And you could stop there because where are we in our picture? If the trace is 0, the determinant is positive, puts you right there. So this is going to be a center. Good. So we know that that's a center, and that's a saddle. Excellent. All right. Now I should say I didn't really finish my method of null claims. Can I go ahead and finish that? Let's see, how would I finish that? Let's get some directions on these arrows or on these lines here. For example, x equals 0. If x is equal to 0, what's happening? What's happening is that x prime is 0, and so y prime is either positive or negative, and so that means you're either going straight up or down. Of course, we know that that's a saddle. Do I know which direction things are moving? Did you say yes? We know that they're moving this way. That's a way you could double check. How about y equals 0? With y equals 0, in this case, this is our lambda equals minus 3/4 direction, and so things are going to be moving in that direction. Good. All right. I think that's all we need. Let's take a look at another online plot of this. Before we continue, I see I got my axes incorrect here. Let me take another sketch of this just to be sure that we got that. Let's do a bigger sketch down here. We have our x equals 0, our y equals 0, our y equals 2, and x equals 3. Okay, and then we have our equilibrium here and here. Okay, and so this is x equals 0, and y equals 2, and x equals 3, and y equals 0. Good. All right. So now, can we draw in our lines here? I just kind of put these in without really doing the analysis. But let's see if we can do the analysis here. So what happens along this line? Along x equals 0, you can see that x prime will be 0, but y prime will be minus 3/4 y. Right? So along this line, y prime is minus 3/4 y. And so that's negative, right? So that's going to be going down. And then this one will be going up. So I got my direction incorrect on that one. And so how about this other direction where y is equal to 0? If y equals 0 in this top one, we just have x prime equals x. Oops. And so that means that if x is positive, we're going to be moving to the right. Good. And if x prime is negative, we'll be moving to the left. Very good. All right. And then how about at y equals 2? What's happening there? Y equals 2 takes x prime equal to 0. Right? And then if you plug that into the second equation, what do you get? Y prime is equal to, well, it's just going to be 2 times minus 3/4 plus 1/4 y, or 1/4 x, right? And so that's going to change at x equals 3. And so if we put in a number bigger than 3, like 4, into that, right, that would be minus 3/4 plus 1. And so that would be a plus. And so we would be going in this direction. Oops, we're moving up and down, right? Good. So yeah, so if x is bigger than 3, we've seen that this guy's going to be positive, and so we're going to be going up. And then if x is between 0 and 3, or if x is just less than 3, so for example, if x is 0, right, then y prime will be negative, and so this will be going down. Good. And then how about along x equals 3? Along x equals 3, our y prime is 0, so we'll be going side to side. And of course, to be consistent, what's going to happen? Yeah, we're going to need to be going to the right, at least below. Let's see if that's correct. So if x prime is equal to 3, our y prime is equal to 0, and our x prime becomes 3 times 1 minus 1/2 y. Okay, so if y is less than 2, so if, for example, if y equals 0, then our x prime is positive, so we'll be moving to the right, like we anticipated. And then if y is bigger than 2, we're going to be moving to the left. Can you still read that? Sorry about that. Maybe make that bigger. X prime is equal to 3 times 1 minus 1/2 y. Yeah, so that'll be going that direction. Can you see what's happening now? Because we've already called this a center, and this is a saddle. And so you can see that's what's happening. Looks like we're getting some solutions like that. Now, I should say for a nonlinear differential equation, or for the linearization, you can't guarantee that the center is going to be a center for the nonlinear case, because the center, or the going from linear to nonlinear, means you're perturbing the system a little bit, you're shifting it, and it doesn't take much of a break to make a center into a spiral. And so you do have to be careful that the center persists going from the linear to the nonlinear case. But in this case, it does. And so now we have a beautiful example of what kind of is this? Is the predator-prey example. Good. All right. And this is kind of interesting because you do see these cycles in nature, and the site where the cycles are not seasonal in nature so much. Because this is not, remember that this is a non-autonomous differential equation. So seasons are not being taken into account here. Good. Okay. So I'm going to stop there. And then the next question, or the next video, we'll try another like full problem from this latest material.